Introducing Boreas, AmadorUAVs 2022 flight vehicle. This year's drone has been designed from scratch to balance design effectiveness and quality while maintaining a strict manufacturing budget.
I'm Kalyan Sriram, President and Team Lead of AmadorUAVs, and welcome to our FRR for the 2022 SUAS competition.
Our team has actually been preparing for the SUAS competition for over 2 years, but this year we'll be attending for the first time. With the exception of mapping, our team plans to perform all mission tasks with a high level of confidence. But first, some information about our drone.
It is a coaxial octorotor, and we chose this design because we needed 8 motors for redundancy and extra thrust so that the motors would run at lower RPMs, so they'd be more efficient. With the arms mounted along the edges, and that opens up the entire center of the frame for electronics. And we have our flight controller, and on each of the 4 sides we have ESCs. Onto these 4 standoffs will go our battery plate. And on the underside we have our auxiliary plate. All other peripheral devices like the servo release here, and in the future our gimbal will be mounted onto the auxiliary plate.
Our team's developmental testing began largely in the summer of 2020, with various mission tests containing waypoint navigation, imaging, and payload drop tests on our known good drone system, Macron. Macron's onboard hardware effectively reflects Boreas' current configuration, where we've gathered nearly 100 hours of sustained flight time for system reliability. During our team's build meetings, our team chose to perform motor thrust tests on our test stand to characterize performance and ensure in-flight reliability.
So this will ramp from 0 to 1000. What we're doing right now is we're running this motor on the motor test stand. So this one has had like a little bit of misalignment issues, I think.
However, through our testing in the field and on the stand, we discovered our first choice of motors was unreliable due to a critical motor shaft breakage issue due to lateral forces induced by wind, an unacceptable risk in production. As a team, we decided on an alternative, T-Motor MN601S 170 kV motors, which have performance characteristics nearly identical to our previous SOAR motors. Additionally, our team also utilizes 3D printing to facilitate iterative design for all of our custom components. While we performed multiple manual flights before sending the drone on autonomous missions, out of the 10 fully autonomous missions we performed, there was no time spent in manual mode. Prior to flight, we calibrate all onboard accelerometers, magnetometers, and gyroscopes. Autonomous flight characteristics, such as maximum speed, tilt angle, ascent and descent speed, are preset before each mission. Extensive tuning of PX4's PID controllers and filters was conducted to ensure optimal performance of Boreas. We utilized PX4's new auto-tuning feature to get a baseline tune of the rate controller. We then further applied small manual adjustments of the rate and altitude controllers to improve responsiveness. We analyzed all flight logs with PX4's flight review tool, which allows us to visualize the tracking accuracy of each controller. PX4 Flight Review additionally runs a Fourier analysis on the drone's angular rate and acceleration data, allowing us to view the vibration profile of the airframe. Using this, we tuned PX4's low pass and notch filters to effectively attenuate vibration and enable smoother flight characteristics.
We ran a multitude of missions on Boreas, both simulated and in real life, measuring various data to verify our mission path planning system. Using PX4's flight review tool to analyze the flight logs of each real-life mission, we were able to conclude that our system hit 73 out of 73 total waypoints with a mean waypoint error of 0.9 meters. We avoided 20 out of 20 total obstacles with a minimum obstacle clearance of 3.4 meters and traveled a total distance of 2,100 meters. The pilot simulation results further validated the efficacy of our missions with even more data. 465 out of 465 total waypoints hit with a mean waypoint error of 0.4 meters, 90 out of 90 total obstacles avoided with a minimum obstacle clearance of 5 meters, and a total distance of 50.5 kilometers traveled. The pilot path planning system was stress tested against various edge cases, such as overlapping obstacles, obstacles covering entry points to surveys, and unavoided paths going out of geofence, to ensure that virtually all of them were handled. These were then further validated on both simulated and local tests. We also ran hover tests to measure waypoint accuracy for hold maneuvers such as the airdrop task, verifying that our system can hold position to within a meter of accuracy. Our pilot path planning system works by taking the mission map and projecting it to a Cartesian grid, allowing us to work more easily with the data geometrically. After this grid generation, we create a polygonal bounding fence around each obstacle to simplify its representation on the grid, and then we are able to run the A-star path planning algorithm to find the optimal path between waypoints that avoids obstacles and remains inside the geofence. This path is then post-processed with various path compression algorithms to ensure that our autopilot is not overwhelmed with too many waypoints.
Our imaging system consists of two main components: Photographer, which runs on board the Jetson on our drone, and IMS, which runs on our ground system. The pipeline starts at Photographer, which takes images from the drone camera, attaches metadata such as the latitude and longitude, and pinpoints each ODLC on the image in order for IMS to identify the location of each ODLC. This metadata and the image is then sent to IMS, where first autonomous classification models are run on each ODLC in order to fill in the attributes of each ODLC. Then, once the autonomous classification models have been run, the final image data actually gets passed to a human to verify the accuracy of each ODLC. By using a hybrid approach, we believe that we will ensure the best chance of success for the imaging stack.
Once we're finished training the autonomous models, we test them out individually. We pay attention to statistics such as mean average precision, and recall while training. But after we train, we test out the models on testing sets that are pretty similar to training sets as well. So we test them out individually. So for the location model, we test them out on images that have maybe 10 or 20 objects in them. So this is from the point of view of a drone 300 feet in the air. Whereas for the subsequent models like character detection, shape detection, and orientation detection, we test them out on zoomed in objects. And again, we pay attention to mostly the same statistics. So for pinpointing, that's mean average precision, which is a measure of overlap between the predicted bounding box and the actual bounding box. Precision, which is a measure of, out of all of the predictions that the model has made, how many are correct. And recall, which is, out of all the correct answers, how many times did the model predict correctly.
To achieve our Wi-Fi link, we are using a directional antenna on the ground and an omnidirectional antenna on the drone. We decided to build a 2-axis antenna tracker system, which was able to accurately point the antenna at the drone while allowing another flight line member to further manually classify images.
To guarantee the best chance of success at the imaging task, our photographer module on board the drone both logs images to the SD card on board the drone, as well as transmitting it live using our Wi-Fi link. That way, even if the Wi-Fi link goes down or has issues, we can always pull images off of the physical storage from the drone. Yeah, so currently we're conducting a drop test. It's manually controlled by the RC radio. We've got the UGV up there. There's a winch on there. It's controlled by the switch. We can unwind it and we can actually rewind it if the thing lands upside down or gets stuck in a position. You just start dropping, it will like run slowly and then stop. Oh, okay.
So the results from these tests were that rheostatic braking turned out to be pretty inconsistent. Accuracy was also acceptable. Most of our drops were within 10 inches, and the average of our 10 drops was about 5 inches off target.
So we're out in the field here, one of our flight test days. So today we're going to be trying a full integration test, dropping the payload, UGV, antenna tracker over there, and then also doing a full ODLC mission and seeing if we can do everything. So we're just putting on props right now and configuring some power monitoring parameters, and then we'll be on our way.
The partial tests we performed focused on testing the capabilities of Boreas to fly missions, utilizing our pilot system to generate paths from interop missions and testing Boreas' capabilities. Our full tests included a test of the path generator, all ground systems such as our antenna tracker and server, and the airdrop task. Using both our developmental testing and full mission test to evaluate our confidence on each mission task, we estimate our mission score to be as follows.